now at CEST Trieste, same place as I'm, except now at home. Okay, Janka, are you at CESA now or at home?
At home.
Okay, from home. Okay.
Yeah.
So he will speak about modular curvature and Morita equivalence. So please, the screen is yours.
Okay. First of all, I'd like to thank the organizers for the invitation. So it's a great honor to have the chance to share something with the audience. So, okay, so let me just adjust my screen a little bit. So again, so I think my talk is, I think it's very somehow close related to Masu's talks. So, and so the title modular curvature and Morita equivalence is borrowed from one of the papers. So I'd like to talk in detail today. So by Moscovici and Lesch. So as mentioned, suggested in Masu's title, so this mysteries of curvature. So probably after my talk, so if I do a good job, probably it will make you more confused about this curvature. So okay. by bringing this Morita equivalence, so let's see how this goes. So probably presentation more a little bit. So okay, so I was the first slide is the main the sort of the spectral approach, right, to get a curvature. So in our non-commutative geometry setting, so this heat trace asymptotic has been discussed quite extensively in yesterday's talks and just in Masu's talks. So the spirit, right? So after dualizing the manifolds to an algebra, which is the functions, right, on the manifolds, the way we implement or we get touch the so-called Riemannian metric is through a geometric operator, a Dirac type operator, or the Laplacian type operator, right? So which is sort of a canonically associated to the metric. So and then to extract the invariants like intrinsic curvatures, like the scalar curvature, Ricci curvature, and more higher order derivatives of the matrix. So we look at the coefficients of this heat kernel asymptotic. So here is the basic examples. Like if we take the geometric operators to be simply the scalar Laplacian, the first term is the Weyl term, which somehow. So if we look at this functional, it's simply the up to some universal constants is the volume term, and in the second term, so this so-called the functional density in here, so we can capture. So sort of it provides a model to get touch to the scalar curvature, right? So that's and again this sort of spectral formulation so proceeds like smoothly into this into our spectral triple setting, I would say so. So now, I mean, my focus of the talk is sort of so now basically the first step is, right, so give you a metric G. So how do you find this Laplacian type operator or Dirac square operator, right? So that's the sort of the first steps. So we like to do. So that's my focus on of the talk. So, and moreover, I will do more concretely. I will just focus on explain like even we just perform conformal change of metric, right? So what's and how to pass from the metric to the geometric operator. So I will focus on the two classes of examples like noncommutative tori and the toric noncommutative manifolds. So as well as known now like theta deformations or Connes-Moscovici manifolds. So I think for the more step, I think that the subtle part I like to explore today is to how to change inner products. So often, I mean, so because of for example, like the Laplacian or this is sort of this d times this d star, right? So the adjoint. So basically, I think these underlying inner products, playing a crucial role in the construction in here. So probably I don't have time so to touch the last part. So I think my first work comes into this project is to somehow to construct a pseudo differential calculus similar to Connes on noncommutative tori, so that we can sort of study the spectral geometry on this theta. So since this the theme of the talks is a kind of a review talk, so if I don't have time to touch my own work here, I think it should be fine. So the main focus I would like to share is the sort of the curvature, like Masu, like give a very fantastic introduction to this curvature, and bring in this Morita, the role of this Morita equivalence. So okay, so here, yes, the construction here is the inner products. I think that's some subtle part that I'd like to share today. So, oops. Okay, as usual. So even though Masu just did review these basic notations on the tutorial, so in his talk, so I'd like to quickly go over our notations. Here, the left-hand side here is the sort of the classical part, right? So here, the right-hand side is the non-commutative part. So basically, if you take the theta, the deformation parameter to be 0, and then, for example, this uv somehow corresponds to the coordinate functions on the two torus, which is e to the ix, e to the iy. So where this non-commutativity comes in, this Weyl commutative relation, right? UV is equal to some lambda, which is e to the 2 pi theta VU. So general for smooth functions on the two torus, we have Fourier expansions of this form, right? So similarly, like for smooth non-commutative two torus, so elements just a sum of a polynomial in this U and V with coefficients of rapid decay which reflects the smoothness, right? So in this integer parameters n and m. So here the involution in the classical case is just because they're complex value functions, we just take a conjugation. While here the involution is defined by this on the generators, right? UV, they are unitaries. So and then we can extend this involution to general elements of this form. So and then the partial derivatives corresponds to the basic derivations on non-commutative two torus. So defined on generators is like this. So here is the formula for delta 1, and similarly formula holds for delta 2. So this corresponds to there is a coefficient minus I in front to make it a self-adjoint. So if you consider partial derivatives, so when you take it for the adjoint, you get a minus sign. So we put a minus I to get a self-adjoint. So that's basically the differential structure, right? So this differential structure is it's represented by this sort of the algebra of differential operators generated by basic derivations with coefficients in the smooth in the algebra of smooth functions. So that's sort of the smooth structure. And on the other hand, so we have when we do calculus, right? So we have differentiation versus integration, sort of these are measure theoretical aspects. So this integration, the notion of integration corresponds to a function or trace or weight. So on the algebra. So here the canonical. So this for the Lebesgue measure, so it corresponds to the canonical trace on non-commutative tori. So if we take a sort of a Fourier expansion, so this integration just catch this grab the constant coefficients a0, 0, and so once we have a volume function or a trace, we can using the standard GNS construction, right, to construct a inner product, and then we do completion. So to get a Hilbert space. So and the classical counterpart is just the L2 function. And so questions so far? Okay, so this is the sort of the structures for functions. So when we build up the spectral triples, so this degree 0 part of the Hilbert space. So now the degree 1 part of the Hilbert space. So as Mansu just mentioned, we are looking at the model of a double Laplacian. So which somehow the differential goes from functions to actually to 0, 1 forms. So here the left-hand side is the standard, like the Euclidean torus, right? So and then we have such a map to a complex torus. So and then you can pull back to sort of the corresponding coordinates, right? So to pull back the complex structure more precisely, the Cauchy-Riemann operators, right? So to move from the complex torus to our Euclidean torus. So then we find the analog of this Cauchy-Riemann operator on non-commutative tori. So here tau is the parameter on the upper half plane which parameterizes all the complex structures. So now this tau and the tau star plays the role of a d-bar operator and its adjoints on Riemann surface. So okay, so now it comes in the role of 0, 1 forms. Let's consider this so at a level of an algebraic level. So let's consider just say finite sum of the finite sums like that, a delta of b. Here delta think of it like a symbol. Think of it at this stage like a Taylor differential forms, like universal differential forms, right? So now delta could have resembles a derivation. So it could at this level, algebraic level, it can represent any sort of forms. So why this is the analog of 1, 0 forms. So the essence here is defined by the inner product on the space. At algebraic level, there's not much difference. So the way, so what kind of forms are they correspond to? So we are looking at such an inner product. How do we define the inner product on 0, 1 forms using sort of this underlying Riemannian metric? So okay, so this is actually not a completely trivial fact. So I think Connes spent a lot of time on this. So this inner product, so details is explained in Connes' book. So for such a section, so it makes use of this so-called positive Hochschild cocycle P, given as below. So this is a Hochschild cocycle. So here the positivity just means that using this cocycle, if you define this inner product on elements like that, so this inner product should be positive. So that's the definition of this of the positivity of the Hochschild cocycle. in this way. So it corresponds to the Masu's talk. So the question of, so we know that on Riemann surface there is a one-to-one correspondence between the complex structure and the conformal structure, right? So how does this result reflect in this sort of in this purely functional analytic setting? So this idea explained in Connes' books goes as follows. So now, so it is captured. This two structure is linked by this such a Hausdorff two co-cycle. So it considers the co-cycle the class of this Hausdorff co-cycle. Okay, so it's sort of a vector space, right? Because it represents the class of a in a cohomology is some representative plus the kernel of something. It's a linear space. Now this sort of a conformal structure reflects in this positivity. Okay, so now the complex structure is reflects in this. So this class can be think of as the functionals on space of matrix. So this part you have to read the Connes book in detail. So this class, think of that the dual space of some moduli space of matrix. So the complex structure is represented by these are the extremal points. So now they agree. So on Riemann surface and on noncommutative. So that's the discussion of Connes' book. So I think he explains in his book. So in this way, so you get a complex structure like to capture the complex structure by solving some optimization problems. So okay, so here the thing I was mumbling about is just the correspondence between the conformal structures and the complex structures in this using this Hausdorff co-cycle stuff. I think so. But so what's important for us is that using this Hausdorff co-cycle, we can define the corresponding inner product on one forms. And more importantly, so this inner product is invariant on the conformal change of the metric, which is which is much easier to understand in a classical setting. In a classical setting, the corresponding result is that if you do a conformal change of a matrix, so the inner product on the middle dimension forms is invariant, because here we're in dimension 2, so the middle dimension is dimension 1, right? So 1 forms. That's why the 1 forms. So the inner product of 1 forms is invariant under the conformal change of metric. So then we don't have to do anything about so this inner product on 1 forms. So later, so to pass from a flat metric to a curved matrix. So any questions so far? Okay, so now then we have so now think about this partial this partial is the partial in 1 forms. So this now you can think of as this an unbounded operator, right? A sends to partial A is from functions to 1 forms in here. So and here it's the adjoint, right? So since we talk about the inner product on functions and inner product on 1 forms, so and then the adjoint makes sense. So in this way, we have a flat spectral triple. Right? So this reflects somehow the flat geometry. So here is an example of this Hausdorff co-cycle on the case of the Riemann surface. So corresponds to the D-bar operator. So okay, so now the next step is how to perform, right? How to construct this conformal change of metric. So like a step by step. So we have something represent some flat some spectral triple represent the flat metric. So now, okay, so here, so I want to explain a construction resembles this this conformal change of matrix by a Weyl factor of the form e to the minus h. So the starting point is that we change the volume form. So we know that if we change a metric by a Weyl factor, so basically so that's how we rescale this volume, right? So and then so here, so the tricky part is that this after this rescaling, so the new feature, which is purely due to non-commutativity, is that this new volume phi is no longer a trace. So the failing of the trace property is somehow measured by this Tomita operator, so or this we call it this modular operator. So, but anyhow, so but the GNS representation still works, right? So that's the so we can still form the GNS representation to get a new Hilbert space. So now the difference between the commutative word and the non-commutative word starts in here. So in the commutative word, so this representation of functions as multiplication operator from the left and from the right. In the commutative case, there's no difference. I mean, even you do this rescaling. However, now in the non-commutative case, if we somehow, right, so if we're using the GNS construction for this non-trivial weight phi, so the left multiplication is still a star representation. So now the similar property fails on for the right multiplication. So that if you consider the right multiplication by functions, is no longer a star representation, because the star operator is modified because of we change the inner product. So the way to fix this issue is to bring in using this Tomita antilinear unitary. So to define a new right action, the new right action. So to correct this, so that now, so this h of phi is a bimodule. Is a bimodule of this a theta non-commutative torus. So the important thing, I think, is even even at a measure theory level, so this geometry is like changed in a really subtle way. So because as a sort of a vector bundle, probably if the change of this inner product doesn't matter, but if you think of as the Hermitian vector bundle, right? So you have to think about this Hermitian structure. So this change of the inner product is quite a significance. So okay, so to summarize this, the subtlety here. So now we are having two choices. So we have two modules. So after this change of metric, right? So after figure out how to change the inner products. So now we have two choices of spectral triples. The one, so using left multiplication, is a usual spectral triple. So if we use the right multiplication, defined by by this correct right action, right? Because we modify the inner product here. So now so we have a sort of so-called a modular spectral triple or twisted spectral triple, which means that so here the twisted commutator is bounded. In this usual spectral triple, the usual commutator is bounded. So okay, so now this this is indeed modular spectral triple. We like to study the the geometry, right? So I mean, you can do similar things for the for this spectral triple. Probably is less interesting. I haven't tried that, so I'm just saying that. So in a work of Connes-Moscovici and in a work of Masu and Fazas, so we work with this modular spectral triple using the right action. Okay, so conceptually, so this conformal change of metric is done at this step, but well, since this D is quite abstract, right? So because this partial is simply a symbol, so there is no way to do computation, right? So, but this is conceptually done, but in order to carry out explicit computation, right, to study, for example, the heat trace asymptotic, so we need to change the Hilbert space. So we want to change this HV and H10 to the Hilbert space H0, on which we have the all the nice differential operators delta 1 and delta 2. So
excuse me.
So yes.
Excuse me. So at this moment, the only difference is in the algebra, yes?
The difference between what?
Between these two spectral triples.
The left and right.
Yes.
So the up and down, right? So
up and down, yes. So
yeah, yes. So in this one, I'm using the left modifications acting on the Hilbert space.
Mm-hmm.
So
Okay.
on this one, I'm using the right modification, which is defined by this sort of the twisted right action. So
okay, I see. But the operator is the same.
Oh yes, operator well, because it's right action, so you have to use this opposite algebra, right?
Mm-hmm. Okay.
So, but the representations are different, right? The algebra is
sure.
Yeah.
Okay, thank you.
So okay, so here, so we can identify with this phi, HV and H0, because so they are the sort of the same as a vector space with different inner products. So it's this identification is not difficult. So you just correct the corresponding the volume. So and then for on forms, so it's here is slightly different from the Masu's talk. So in this Ricci curvature, so the forms, they are identified with direct sums of H0 and H0. In this case, we can just identify with these 0, 1 forms with H0 by replacing this formal delta by this Cauchy-Riemann operator delta. So and the crucial part is that this is a unitary identification, and it preserves this left and right actions of non-commutative torics. So in particular, this bimodule, right? The right action is the one like twisted by this tomata anti-unitary. So this is a unitary and preserve this bimodule structure. So the next step is that so we do not want to work with this right action. So then the next technical part is to sort of take the transpose, so that we can. So because we want to study this modular spectral triple, right? So we take transpose, which means that we take for Hilbert space, we consider its dual or its complex conjugate, because a Hilbert space has an inner product. So it's sort of the self-dual. So we take the transpose, so that in a way, by taking dual, so the left actions becomes left actions. So that's the next step. Transpose of a spectral triple. So we're using inner product, so to identify H with its complex conjugate or its dual space, and then an operator becomes its transpose. So by conjugation using star and the conjugation. So by this anti-linear isometry. So in particular, in our case, this is an abstract setting for general Hilbert space, right? So in our H0, this inner product is associated to the GNS representation, a GNS construction. So and then this JH is the Tomita anti-unitary, but not the Tomita anti-unitary I mentioned before. That one I call J phi, right? So that is the anti-unitary correspond to the phi. Now this is the anti-unitary corresponds to the phi 0. So in this case, this is quite easy. You just extend this star A maps A star to the whole Hilbert space. So and then to put two copies for this J. So one copy is J, the other is J minus. So and then so this is the sort of the taking transpose. So and then one has to do some straightforward computation, right? So this W so helps to change the Hilbert space from H phi and H10. So after all, this will all change to H0. This all change to H0, and then this J change from H0 to H0 the dual, right? So that we are looking at there's no up here, so we are looking at the left action. So this transpose modular operator, right? So the transpose take care of this to get rid of this up, as we had a few seconds before. So and then we can so we can compute the Laplacians of this form. This is the Laplacian on functions, and this is the Laplacian on one forms. So any questions so far?
So actually, so this formula for this D bar psi appears in Connes-Moscovici probably, right? In this paper.
Yes, this
looks quite different from other, let's say, expressions, but you explained how they really got it, yeah, with details.
Yeah, yes. I think at least this one, I think it's the same as the one used in the Masu's talk in the first part, right? So this.
Okay. Thanks.
So okay. Oh, so by the way, so in the middle of the Laplacian is the flat one is like delta 1 square plus delta 2 square. So very simple. So isospectral to the commutative case. Okay, so this is the. So okay, so. So okay, so now with this with the curved metric represented by this modular spectral triple, so how to grab some invariants or intrinsic curvatures. So as Masu explained in his talk, so we look at the spectral zeta functions. So and then so the Gauss-Bonnet theorem, so it's just saying that consider the functionals, so which is the functional defined on this class, the class of conformal, the class of metric, conformally flat matrix, right, parameterized by this log-Weyl factor. So this H, this function is sending H to its corresponding to the value of a zeta function at 0. So recall that this H depends on this phi, the function of phi depends, this volume phi depends on this H. So this functional is a constant functional in H, which resembles this integration of scalar curvature. So it's constant it's independent of the metric. So that's the statement of the Gauss-Bonnet. So okay, so now if we look at this functional, probably not interesting. It's constant functional, and then what's the next step, right? So and then the value at the zeta function is constant. Then we look at the first derivative. So it's the Ray single determinant. So and then we do a sort of a normalization. So plus a log of this. This is sort of you should think of as this divided by some volume because it's taking log, right? So this log turns the division into subtraction. So this basically you divide it, just normalize the volume so that the functional has a maximum and minimum. So this is the so-called OPS functional used in the paper of Osgood, Phillips, and Sonark. So we're on which like the Connes-Moscovici took this as the model in a commutative setting to non-commutative two-torus. So basically the key ingredient here is the Ray single determinant, which is by definition is the derivative of the spectral zeta function at 0. So this goes back to, and then to define the curvature is defined using this variation principle. So then we consider this variation problem. So if we we perturb this metric, so this is H is sort of a parameter at the tangent space of the metric, right? So because e to the H, the conformal factor represents this H. So H is sort of at the level of the tangent space. If we do a perturbation, so move it along some other direction, A is another self-adjoint element here, right? So put the parameter epsilon, and we consider this variation. So and then we take derivative in epsilon and evaluate it at 0. So this is a linear function in A. So by heavy computation, we can show that this linear function is sort of local in a sense that it can be written as the integration of A with some density. So this density we call this functional gradient. So this gradient of this abstract functional. So it's very similar to what we learned in calculus, right? So this is the way you graph this sort of the directional derivative. So and then we call this this modular Gaussian curvature, whose formula has been explained as, in great detail in Masu's talk. So the explicit formulation involved this this complicated functions from rearrangement. So this is not my focus on the talk. So here is the definition of the Gaussian curvature on non-commutative torus associated to the modular spectral triple. So okay, so now the next step is to bring in this Morita equivalence. So think of our discussion just before is like a sort of intrinsic no twisting bundles. So somehow the next step I'm going to do is to introduce some actual sort of very famous vector bundles on non-commutative torus. So the so-called Heisenberg modules, which implements Morita equivalence between the A theta and some A theta prime, which I will write it down explicitly in a second. So to do that, so let me review the sort of another construction of a non-commutative torus, so which relates to this so-called the Heisenberg representation. So you think of R and G as R cross R, so two copies of R, where the second copy viewed as the duals, Pontryagin dual of R. So now you put the Lebesgue measure and it's the corresponding Poincare measure on it, so that G becomes a self-dual and with a bi-character rho, so defined by in this way. So here the brackets just means that this is the natural evaluation, right, between R and its dual. So here cocycle E is defined in this way. So here is the classical Heisenberg representations. So you can see the R2 acts on L2 space of R1. So this R acts on itself by translation, while this R dual acting by multiplying by, because R dual viewed as there are characters on R in particular, that they are functions on R, right? So there are L2 functions. You can just do in multiplication. So this is multiplied by the characters defined by Y2, and this acting by translation. And then, so this is not a representation, it's a projective representation, because if you look at the composition of pi x and pi y, it's not pi of x plus y, but with a cocycle E. And then using this relation, you can easily check that so we obtain this wire commutative relation, right? So pi of x composed with pi of y. If we switch the order, what happens? What happens? We have this E of xy and E of yx with a conjugate. So which by definition is the rho here. So in a way, so this rho will give you this e to the 2 pi I theta in the definition of non-commutative torus. So here, so the standard recipe in representation theory is that so once we can integrate this representation so into a representation on the Schwartz functions on R. So here, so here by definition is in the following way. So here I put a here, it means that the algebra structure is not pointwise multiplication, it's the convolution twisted by this cocycle. So this multiplication is defined by whatever, so to make it to a representation. So you can write down the convolution using this formula. So this is the standard exercise in this harmonic analysis. So then how to recover a theta is just you basically, so now you have a function, a Schwartz function on R, you just restrict on some lattice. So basically, so for any theta, the theta is the parameter in a theta. So you find a nice embedding, find a lattice nice embedding, so that this row of xy gives you exactly the e to the 2 pi I theta. So now you just restrict a function on the lattice. So then you get the elements in a theta. So that's the explicit correspondence. So L has two components, right? L1, L2. So these elements are functions restricted on the lattice, and then this is a function in a theta. So okay, so and then to get a Morita equivalence. So now we have a theta and a theta prime. So a theta prime is given by a linear fractional transformation from a theta. So the transformation is implemented by a elements in this SL2Z. So this so in general we can construct Heisenberg by modules like this. So basically, you find a lattice associated to a theta and another lattice associated to a theta prime. So they are perpendicular. So so they are perpendicular in respect to the bi-character row. So and then this is the corresponding actions, right? So you can see that this is basically a very sort of a modification of the Heisenberg representation. So this is U1 acts by multiplying by this character, while U2 acts by translation. So it corresponds to by choosing this embedding of lattice, right, in different way, right? So because we have a theta and a theta prime, so we get this left well, this is the right action and this is the left action. So we have the bimodule structure of this Heisenberg module. So in analogy with algebraic geometry, so we defined the notion of rank, degree, and their quotients. So okay, so again, what's important to us is somehow this inner product. So now, so this the crucial ingredients we like to use from the Morita equivalence is the following. So we have now we have three inner products. So in the definition of Morita equivalence, is the one is the inner product with value in this right algebra, right? So it's bimodule in A theta. Well, another one is in the left algebra, A theta prime, and the middle one is the classical L2 inner product. So you should the geometric model, you think of this as a probably I should. So the analog you think of, so now you have a vector bundle. So a Hermitian vector bundle on a manifold, right? So you take two sections. If we take the fiberwise inner product, so it's then you get a function on the manifold, right? So this is while on the other hand, so if you identify with this S tensor with S tensor, it's dual using the inner product, and then this is you get the matrix, right? So you get a matrix. So now you get so I will write S transpose times S, you get the matrix. So probably I think it's the other way, right? So S times its transpose, you get a matrix in this endomorphism. So this of E, this sort of say this is a theta, so this is something like a theta prime. So this property is non-trivial to check. So it's making use of a Poisson summation formula. So to get this formula. So
sorry, Yang, I mean, is this associativity equation the one that you underlined? I mean, because
here,
yeah, there is always an associativity equation which is very important. This Morita context to establish finite generation and projectivity.
I think I skipped this associativity question because I want to focus on the inner product.
Yeah, that's also related to I mean to this to Poisson summation formula. Yeah.
Yes. So the proof is to use these associativity condition plus the Poisson summation formula, so that you can you can derive this property, which links three inner products together.
Yes.
Turn off my so okay, so let me erase this this scratching. So here. So yes, thanks. So I think Masu's question is very crucial. I think I will use this the associativity in a moment. Okay, so now basically we shall go over we shall go over a similar process of conformal change of metric as before. So now the Hilbert space. So this is the Hilbert space on
on functions. So I will tensor with the sections of the vector bundle, right? So and then doing completion. So I use this E, capital E for for L2 space. While if I'm using the curly version, then it's like it corresponds to smooth sections without like before the completion. So yes, so we tensor the functions and the 1-0 forms with the sections of Heisenberg modules. So we get our new Hilbert space. So, and then we have to extend the connections, right? So we have to differentiate the sections. We need a notion of connections. So this notion of connections can be derived by differentiating the projective representation of R2 we mentioned before. So the projective representation of R2 is equivalent to a representation of the Heisenberg group. So by differentiating this action, we get two differentiations. So this delta 1 and delta 2 corresponds to the generators of the Lie algebra of R2. So and a similar to the construction of the Cauchy-Riemann operator, we consider this partial epsilon. So we take a combination of delta 1 and a delta 2 with the complex parameter. So this sort of this holomorphic connections satisfy the usual property, right? So this is simply the Leibniz property, right? So it's the derivation property, right? So I put it together like with the left and the right modules. I hope you can see that this is nothing but the Leibniz property. So small things that so we have to normalize. So because of some inner product, something like that, we have to normalize. We have to normalize this derivation a little bit in here. So this is the derivation property, and it also satisfies the compatibility with the with the Hermitian structure here. Right, so this is the compatibility with the derivation and a Hermitian structure. So I wrote this component wise, but the similar thing holds for this this sort of partial E. So again, so now we consider the action of A. We have a right spectral triple in here, represented the flat matrix. So because we have not yet changed the inner product yet. So the crucial thing, so I'd like to point it out, is that this Laplacian now here is sort of it's easier than the Laplacian I just mentioned before, in a sense that it is just a genius harmonic oscillator. It indeed acting on functions on R, because our underlying, so here our underlying Hilbert space is so our underlying Hilbert space is function on R, right? So now think of the previous delta. So that they act on some abstract Hilbert space H0, which derived from the GNS representation. Now by tensoring with this Heisenberg module, we make this operator somehow easier because it becomes a harmonic operator acting on L2 of R, or several copies of L2 of R. So, well, easier in a conceptual sense. Right? So now we do this conformal change of metric. So yeah, basically the change of matrix happens. The same thing, the conformal change of matrix start with changing the volume form, right? We're still rescaling the canonical trace by a Weyl factor, we get the phi. And then again, so because A theta already acts on the right hand side. So we have to correct the right action by using this this modular operator or the Tomita antilinearity. So okay, so at this stage, so again, conceptually it is done. So we change the inner product on functions, and basically we don't have to change the inner product on forms. So as before, so I think I'm running out of time. Probably I need probably 2 or 3 minutes, Ludwig.
Well, that's okay, yeah, because you started a few minutes later, so you have 4 minutes, yes.
So here, so yeah, so I'm reaching the end. Yes, I'm very close to the point. So I think that will confuse you a lot. So okay, so yes, so now we have this right spectral triple, right? So that's represent a curved metric. Again, so at this moment, for this one we cannot do computation because this Hilbert space is somehow abstract. So because we have this h of phi here, so and the h of 1, 0, right? So again, we use this isomorphism W before. So now to do computation, we just have to change the Hilbert space. We change the Hilbert space to H0, our favorite, because we have all these nice derivations, differentiations. So we use the same operator W to change this h of phi and h of 1, 0 forms. This is abstract forms, so maps to something concrete. So we change the Hilbert space, and we want to take the transpose. So now that the transpose becomes more complicated, so without this Heisenberg module, so we don't have to change the Hilbert space. The transpose, we're making use of this the Tomita antilinear unitary, right? So associated to phi 0. But now this case, we have to take the recipe of taking complex conjugate in this Morita equivalent business. So now this canonical anti-isomorphism changes the Heisenberg module from the parameter with g theta to the parameter of g inverse theta prime. So we have somehow changed the Hilbert space a little bit. So, but anyhow, so we basically, you think of you just take the dual space of the underlying Hilbert module. So you take the dual space so that we can move the right action from the left action. So we have the right action up here from the from the left action. So again, so the tricky part is here. So the elements in A theta, you should think of this as an endomorphisms on a bundle of our Heisenberg module, right? So we do this Weyl factor on A theta is actually an endomorphism on the bundle. So using this endomorphism, we can change the Hermitian structure on the bundle. But thanks to this Morita equivalent business, so we can move. So this is the first highlight I want to emphasize. This changing of the Hermitian structure by the Weyl factor on A theta is equivalent. You change your somehow you change your is some effect you change your L2 inner product on, if you look at this A theta prime side. So using this the compatibility between the three inner products, right? A theta valued, A valued, and this L2. So that's the point. So we should keep in mind. So then I will come back in a second. So okay. So what's the upshot? So the upshot is that we have this operator, this twisted conformally perturbed Laplacian, which acting on L2 functions. And we can consider the same Ray-Singer determinant function, right? So consider the same variation problem to define the Gaussian curvature. So the upshot, so sort of a surprising result in Moscovici and Lesch's paper is the following. So we have the same elements, we find the same elements in a theta, this curvature. So this right-hand side sort of extrinsic curvature, the left-hand side is sort of intrinsic curvature. They do agree in this business. So that's sort of this property can be think of sort of this a little bit invariance property of the Gaussian modular Gaussian curvature under the Morita equivalence. It is saying that this sort of this modular Gaussian curvature, first of all, it is independent of your module. Okay, so this as an element in a theta it is independent of this epsilon theta. So this sort of resembles, so that's a Moscovici's picture. This resembles sort of the fact that if you embed your A theta into the endomorphism of E theta prime, so you do an embedding, so this your A theta into some other algebra. So sort of this modular Gaussian curvature is somehow independent in this embedding. And the other observation is that so somehow this A theta, this conformal change of metric A theta somehow confers a metric on A theta prime. I mean, since it's independent of this eta theta prime, so this the same Weyl factor in A theta, so defines sort of a matrix on a family of A theta prime. These families like all the possible theta prime, which is in the same class as theta. So via this SL2 action, so sort of this invariance somehow gives you, so this curvature somehow it's sort of an invariance for this class of A theta prime. So in this class, so I mean geometrically this class corresponds to this Kroneck foliation. Somehow in this sense, this curvature somehow is something attached to the Kroneck foliation. So I think I'm running out of time. So I think I will end. So that's the end of my talk. So I think I confused you a lot by bringing this Morita equivalence stuff. So I hope, I mean, the point is that I think we can do something for other example like this theta derivation, like to explore this phenomenon of curvature among more examples. I think it's quite interesting.
Okay.
Thanks.
Thank you, Jan. Thank you for your talk. And now we still have perhaps short time for one